Hello everyone, my name is Nikhil Yantrapati and my roll number is 24011A0512. I am from CSC Regular, Section I, and my teacher is Mr. Raju. So today I'll be presenting you one of the most fundamental concepts in electrical engineering, and that is thevenins theorem. So in this session, I'll be covering the following topics: what the thevenins theorem is, its importance in circuit analysis, step-by-step explanation on how to apply it, a practical example, problem solved step by step, real world applications of Thevenin's theorem. So mainly I'm going to be explaining three problems related to Thevenin's theorem, which will help you get a better understanding of the whole concept. So starting with the introduction, what what is Thevenin's theorem? Like what is it? Yeah, you can see the diagram right here, like the basic Thevenin circuit here. You might not understand what it is right away, but let me just break it down for you. So yeah, what is Thevenin's theorem? Thevenin's theorem, it is a method used to simplify electrical circuits. It helps us replace a complex network of voltage sources, current sources, and resistances with a much simpler equivalent circuit. So yeah, that's what Thevenin's theorem is. So let me repeat it again. So it is a method used to simplify electrical circuits. So it mainly simplifies electrical circuit. Like if it's a complex electrical circuit, it's going to divide it into it's going to simplify it and make it less complicated. So it mainly helps us in replacing a complex network of voltages and current sources and resistances with much simpler equivalent circuits. So let me tell you the statement right away. So Thevenin's theorem, it states that any linear electrical circuit which can be replaced by an equivalent circuit containing a single voltage source called the Thevenin voltage in series with a single resistance called the Thevenin resistance. So Thevenin's voltage is called is represented by VTH, and Thevenin's resistance is represented by RTH. All right. So why? So why is Thevenin's theorem important? Imagine dealing with a large and complex circuit which has multiple voltage sources, current sources, resistors, and if you want to analyze the current through or voltage across just one particular component, solving the entire circuit repeatedly, different conditions can be tedious. So you just can't really deal with many circuits at once. So Thevenin's is used to merge and simplify it so that you can work on your problem better. So Thevenin's theorem, like I said, simplifies the problem. By replacing the circuit with its Thevenin equivalent, you only need to work with two parameters then. One is VTH, that is equivalent voltage source. The second one is RTH, the equivalent resistance. This saves both time and effort, especially when testing different load conditions or designing circuits. So steps to apply Thevenin's theorem. Let me break down the steps involved in Thevenin's theorem. So first we got to identify the load resistor, right? So we got to identify the load resistor. Let's move on to the first problem now. I'm sorry, my bad. So yeah, this is the first problem. Just take a look at the circuit. Now, we got to identify the load resistor. First, decide which resistor or component you want to analyze. This is called the load resistor. Remove it from the circuit, right? So one of them is called the load resistor, and we have to remove it from the circuit. So determine RTH. So the next step is to determine RTH. That is Thevenin's resistance. So for that, we need to deactivate all independent sources in the circuit and replace all voltage sources with short circuits. Replace all current sources with open circuits. Now calculate the equivalent resistance of the remaining network. This is called Thevenin's resistance, RTH. Now, now we've got now we've got to determine VTH, Thevenin's voltage. So reactivate the sources, calculate the open circuit voltage across the terminals where the load resistance was removed. This voltage is VTH. Now reconstruct the equivalent circuit. Replace the original circuit with the Thevenin circuit. This will consist of a single voltage source VTH in series with the Thevenin resistance RTH. Reattach the load resistor to this equivalent circuit. Now step 5 is to analyze the circuit. Use Ohm's law or other circuit analysis method to find the desired current, voltage, or power across the load resistor. Now, this is the first example problem. Like I said, we have to follow all the steps which I mentioned previously. So right now, let's apply these steps to an example problem. So we are given a circuit where a 40 ohm resistor is connected to a network of resistors and sources, right? We need to find the current through 40 ohms resistor using Thevenin's theorem. So we need to find the current which is passing through this 40 ohms resistor. That's what we need to do. So here's how to solve it. Step 1. We got to remove the load resistor. Disconnect 40, right? Disconnect 40 ohm resistor from the circuit. This leaves two terminals, A and B. Should be here, right? So when we disconnect the 40 ohm resistor from the circuit, this is going to leave us with A and B, right? We disconnected the resistance here, so it's going to leave us with A and B. So step 2, calculate RTH. We're going to calculate this Thevenin's resistance now. So deactivate the voltage source by replacing it with a short circuit. So here we replace it with the reactor with the repeating of the short. So find the equivalent resistance. Right. So here we found the equivalent resistance here using the formula R1 into R2 by R1 plus R2, as we all know the formulas already. So now using parallel and series combinations, we find RTH. Right. So using the parallel and series combinations, we find RTH, which is I equals V by R, that is 0.33 amperes. That's what it is. So now the step 3, we've got to calculate V. So in order to calculate VTH, we have to reactivate the voltage source. Using Kirchhoff's voltage law, KVL, in the loop, we often open circuit voltage across the terminals A and B. Solving the equations VTH, we get 8.33 V. That is, yes, no, sorry. Yeah, we get it as 8.33 V. We get VTH as 8.33 V, which will later be discussed. So we got step 4 is we're going to reconstruct the Thevenin circuit. Replace the original circuit with the Thevenin circuit. VTH equals to 8.33 V in series with 0.33 amperes. Reconnect the 40 load resistance. So we're going to reconnect the 40 load resistance like we did right here. So it is reconnected, and we're going to analyze the circuit using Ohm's law and using the forms, using the calculations. The current flowing in the circuit, yes, this is going to be the current flowing in the circuit, that which we already know. Yeah. So yeah. So here we got 0.286A, which we calculated previously. There's the current flowing through the circuit. So now, yeah. So now, uh, we're gonna move. We're gonna talk about how we did this. That's completed the calculations, and now we're gonna talk about applications of Thevenin's theorem, like a couple of applications. So Thevenin's theorem is widely used in it is widely used in various areas of engineering such as power systems, electronics, and network analysis. Let's talk about this later, but now let's move on to the next problem. So yeah, in this problem, we've got to find VTH, that is Thevenin's voltage, Thevenin's resistance, and the load current IL flowing through the load voltage across the load resistor in the circuit below using Thevenin's theorem. So we're going to follow this question and break the whole question down step by step. So step 1 is to remove the 5k uh, resistance from the circuit. So I think this is what we've removed from the circuit. And step 2 is to measure the open circuit voltage. This will give you the Thevenin's voltage VTH. Step 3 is to calculate Thevenin's voltage by determining the current that flows through 12k ohms and 4k ohms resistor. The current which flows through here and through here. As both the resistors are in series, the current flows through can be calculated as follows. This is the formula which they use to calculate the current. Now the voltage across the 4K volts can be calculated as follows, and this is also another equation where they calculate how much voltage is in the current. So as there is no current flowing through the 8 kilovolt resistor, there is no voltage drop across it, and hence voltage across terminals A and B same as voltage across 4K resistor. Therefore, 12 volts will appear across the VB terminals. Hence, the Thevenin's voltage VDH equals to 12 volts. Right? So yeah, that's exactly what it means. And step 4, the short voltage sources as shown are given below. So this is how it's given, like the whole calculation. This is what we did it. This is the broken down version of it. Now step 5 is to calculate Thevenin's resistance. That's RTH. By measuring the open circuit resistance, we can measure Thevenin's resistance. We notice that 8K ohm resistor is in series with the parallel connection of 12K ohm and 4K ohm resistors. Therefore, the equivalent resistance or Thevenin resistance is calculated as follows. So this is how it's calculated. Uh, you guys can just take a look at it. So now step 6. Now connect RTH in series with voltage source VTH and the load resistance shown in the figure. So this is the final voltage we get. And now for the last step, we calculate the load voltage and load current using the Ohm's law as follows. This is what we do, and we get the final answer which we need. That is 3.75 volts. Excuse me. All right. So moving on to our final problem, that is obtain Thevenin's equivalent circuit with respect to the terminals of AB of the network shown in the circuit. So this is a circuit which is given to us. So we've got to obtain Thevenin's equivalent circuit with the terminals of A and B, right? So step 1 is the Thevenin's equivalent circuit also can be obtained by, we got to transform the circuit as given below. This is how we transform the circuit. And now we got to do the required calculations. Sorry. So now we've got to do the required calculations. So determination of a Thevenin's voltage. So applying KVL to the closed loop. For the figure B, we have the following calculation where they use Kirchhoff's voltage law, and they get Thevenin's voltage as 8.33 V. So in order to determine our Thevenin's resistance, it's very simple. We just have to divide it. We divide 5 ohms resistor with 10 ohms. We get 3.33 ohms. So that's how we determine Thevenin's resistance here and Thevenin's voltage here. So I'm going to conclude by saying Thevenin's theorem is a powerful tool that simplifies circuit analysis, making it easier to study how a network interacts with particular load. It is especially useful for engineers dealing with large and complex systems. By reducing the circuit to a single voltage source and series resistance, this method saves time and effort when analyzing or designing circuits. The theorem is extensively used in power systems, electronics, and network design, as it provides a straightforward way to model circuits for load analysis, fault diagnosis, and impedance matching. It also helps optimize energy transfer in systems like generators, batteries, or communication boards. For example, in power systems, it can model how voltage changes as load varies, while in electronic circuit design, it simplifies sub-circuit analysis without losing accuracy. So I really hope you guys got something out of this, and thank you for watching my presentation. I hope this explanation was clear and helpful. If you have any questions, feel free to ask me. Thank you.